What's up guys? So today I wanted to talk about iron temperature and how to go about choosing what temperature to use on your tools when you're working with microsoldering. One of the things I want to point out right out of the gate is that there is not like a correct temperature, but there are certainly situations where if you don't have enough experience, using too high of a temperature can cause issues. So in this video, I'm going to try to go over a few different starting points that you can use depending on what you're working on and what parts you're working with. And I'm going to try to visualize it as well with the thermal camera. So you guys can see how the heat sort of travels through different types of boards and on different types of points. And I'm hoping this is going to help a few of you guys who are lost as to what kind of temperatures you should be using when working with various types of boards and various components. So we can't really talk about temperatures without talking about the type of solder that we're working with. So this is the first thing you should take into account: what kind of solder is on the part or on the board that you're going to be working with. And in almost every case, unless you or someone else has worked on that board before, a board straight out of the factory is almost always going to have unleaded solder on the board. The thing to note about unleaded solder is that it has a higher melting temperature than leaded solder like I use here. So the solder I use here is leaded solder. It's tin and lead. It's 6337 solder, and this melts at 183 degrees Celsius. And by the way, all of the temperatures I'm going to be mentioning in this video are going to be in Celsius, and in any other video for that matter, I just always use Celsius. So yeah, this stuff melts at 183 degrees Celsius, but the unleaded solder that's on these boards here from the factory are going to melt at anywhere from like 217 degrees Celsius to 227 degrees Celsius. And while that 30 to 40 degrees Celsius difference doesn't sound like much, it really makes a big difference when you're working on boards with that solder. So right now I have the power supply in view here so you can see exactly what temperature I'm using on the iron. So like I said, this melts at 183 degrees Celsius, and I have this set to 183 degrees Celsius. Given this is not going to be 100% accurate on the tip, but this will still be a lot more accurate than an iron like this that just has sort of like this cover that slips on, and then the tip goes over this heating element. In the case of irons like this, these are really not all that accurate. Whereas with the C245 or C210 style irons like this, the tips themselves actually have the thermistor in them, which is measuring the temperature of the tip. Not to mention that the heating element is actually in the tip itself and not in the iron body like it is with this one. So these are significantly more accurate, and if you want, you can even actually calibrate these guys with a little tip thermometer. One thing I'll say is that if you guys still have an iron like this that has a slot on tip like this one, or if you only have a portable iron, definitely go ahead and pick up something similar to this. I'll have a link to this one in the description. I'm really happy with this one. If you guys are interested in my review of this particular station, I'll have a direct link to the part in my tool video where I talk about this one. So this says 183 degrees Celsius. So technically this should be melting the solder, right? But you can see here, if I tap the iron on this solder, it really is not doing anything. It's not melting. It's not like I can cut this in half or anything or get any of the solder to melt. And it should be pretty obvious why this is the case. We're at the exact melting temperature of the solder. When we're touching things like this, we lose some heat effectively. So obviously we need to compensate for this and move up to something like 200 degrees Celsius. And let's see if we can at least start melting some of the solder now. So yeah, this is starting to melt, albeit a little bit slowly, but it definitely is melting the solder now. So similarly, we'll compensate by going up to 250 for the unleaded solder on the board here that melts at anywhere between 217 to 227. But something you'll notice is that when you're working with solder on a board, the heat is going to spread through the board. And not only that, but depending on the point that you're actually soldering, various traces on the board are thicker or sometimes are actually an entire plane. Like in the case of a ground pad, the heat is going to dissipate pretty quickly throughout that plane, and you're going to lose a lot of the energy from your tip into the point that you're trying to solder. So just to give you a visual example of this, if we switch to the thermal camera here, I'm going to put my 250 degree iron on this unleaded solder point here, this ground point of this Ethernet port. And watch what happens to the heat on the thermal camera when I touch that one little point there. So I'm touching it now, and as you can see, it's really not like heating that point really well at all. It's just sort of spreading the heat through the board. You can see, even if I hold it there for upwards of 30 seconds, we're just going to see the heat sort of slowly spread through the board. And this is because this is a ground plane and it's just pulling all the heat away from that one point. And you can see as soon as I remove my iron, the heat is just sort of spread out through the board. And even more so, if I zoom out here, you can see just how much that heat spread out through that ground plane. It's really not on that one little point that I put the iron on. Now take a look at what happens if I instead put my iron on one of these tiny points right here, which is not connected to a ground plane. See that? See how much more hot that one little point gets because it's only on this one little trace. You can actually see the heat traveling through the trace on the board, and it's not able to spread out nearly as much as when we put it on the ground point over here. See how much more that spreads and doesn't actually go into the point. So this is just a great visual demonstration of how heat sort of flows through the board. And you can see this point here, even though it's just as small, it's traveling through the board a lot more. And this is very likely because this is a ground trace which is going through the board to a ground plane underneath it. So it's spreading the heat out significantly more than these tiny traces here and here would. So really kind of a cool visual example of how heat travels through traces themselves. And it doesn't necessarily have to be a ground plane for it to be pulling heat away from the point you're trying to heat up. Another place on boards where there are commonly larger pads and larger traces is when you're dealing with voltage rails. For example, this point right here on the top is actually the positive voltage rail. This is not ground. This is the positive 12 volts rail for the PS5. And this is also like a pretty huge plane. So if I put my iron here, you can see it's just going to spread out through that entire trace there, or that entire voltage rail plane. And you can see when I let go how much that heat spread out, you can see in that area. So the type of point and how big the trace is on the board that you're trying to heat is another consideration you definitely need to make when you're deciding what temperature to use. So even though my iron is at 250 and is over the melting temperature of the actual solder on the board, because it's on the board and because it's on a ground plane, for example, it's going to spread that heat out. And in order to actually melt that solder, we have to compensate for that heat loss by increasing our temperature. So personally, I'm not really interested in doing math whenever I'm doing soldering, so I'm not trying to find like the lowest of the low that I can use. I just want to be efficient and get the job done. And I don't want to be having to like fiddle with my temperature all the time. And my starting point is generally just going to be 350 degrees Celsius. It's very rare I'm going to be using a temperature under 350 personally. And I just want to mention the important thing about temperature is to choose something that you're comfortable using without damaging or burning components on the board. You'll find that the more comfortable you get with microsoldering, the more comfortable you're going to be with using higher temperatures and just working quicker. It makes things a lot easier. You can just use the higher temperature and, work a little bit quicker with things. And honestly, personally, recently, I've just been using anywhere from 375 to 425. This is sort of my go-to range for soldering. If I'm working with leaded solder on a smaller board, I'm going to be using something like 375. Or if I'm working on components that are more heat sensitive, I'm going to be using maybe 350, but probably more often 375. Otherwise, you're going to see me using 400 or 425 almost all the time. If you're just starting, I don't necessarily recommend starting with temperatures like this because you're probably going to be leaving your iron on things a lot longer, as you sort of start getting used to your tools and things like that. So it is probably a better idea to start at more like 350. And that way you can give yourself a little bit more flexibility with how long you're using, your iron on the board. But as you get more experience with things, you're going to want to be quick in, quick out with the heat. And ultimately, it's honestly much better that way when you're using a higher temperature for less time versus a lower temperature for a longer period of time. So I do recommend getting really comfortable with your tools and steer yourself towards using those higher temperatures so that you can work quicker on the board. Get in, get out, and avoid thermally stressing the boards for longer periods of time. I would argue this point is even more important when you're working with hot air, because with hot air, you are heating a larger area of the board for a longer period of time than you are when you're using your iron. I used to be using, like 350, 375 on my hot air station a lot more. Nowadays, I'm using anywhere from 400 to 450 pretty regularly just to be able to get in and get out quickly with components on the board, and I'm not heating everything around it for long periods of time. Obviously, there are exceptions to this that we're going to go over later in this video, but I did just want to point out that that's especially the case with hot air because you're applying heat for, extended periods of time and larger areas of the board than you are going to be with your soldering iron. All right, with that out of the way, let's proceed with the demonstration here. So you can see this is going to melt this solder without any issues at all. 350 is a great starting temperature for unleaded solder like this, and you can see it has absolutely no issues with that. So let's do the exact same test that we just did, but with the higher temperature, and you can see even more so how the heat sort of spreads through the board. So even at 350, I can tell you right now, this is going to struggle significantly for a few reasons with this particular ground point. But you can see at least it is having a little bit more success with applying localized heat to that point. If I leave my iron on there, as soon as I take it off, you can see it will just disperse throughout the board. And actually the reason for this is the iron here is continually trying to keep up and heat the tip up to that particular temperature while the board is pulling the heat away from it. So this is actually like putting heat or energy into the board as I put my iron on the point. And we'll be able to see this even more so with the tiny point here. It has a lot more luck heating up those tiny points as well. And you can really see just how much that heat spreads through that trace there But now if we try with this point here, you can see the ground point here, or whatever it is, the larger trace I'm heating, definitely still spreading things out, but at least the temperature is sort of compensating a bit. So even with 350, this point is having none of it. Like, none of the solder is actually melting still. And this is going to be for a couple reasons. One of the main reasons is this board is huge. Look how thick this PCB is compared to, for example, this switchboard I have here. Let me just zoom into this so you can see what I mean. The PCB on the PS5 here is super thick compared to this PCB here. And the board itself is actually going to pull heat away from the points you're heating up. Not just the ground planes, not just the traces, but the board itself is sort of acting as a heat sink and pulling heat away from the points. So obviously not only the thickness, but the size of the board too is going to play a big factor in how much heat you need to use in order to melt, especially a ground point like that. So let's try the exact same thing on a ground point on this USB-C port here, on the smaller and thinner board, and let's see what happens. So I'm not going to change the temperature at all on my iron. It's going to be the exact same temperature. And we're going to go to the thermal camera here, and you'll see just how much more effective this same temperature is on a smaller and thinner board like this. So we're just going to apply heat right here to this ground point, and see how much more that heats up that little tiny area there, even though it's still on the ground plane. Yeah, it has absolutely no problem getting this point up to temperature here to actually melt the solder. The solder is actually melting there, and this is just simply because the board is thinner and smaller than the PS5 board. Same goes for this point over here. You can see it's actually putting the heat into that little point. Even though it is spreading out through the board still, it is still able to get enough heat into that point to melt the solder. And let's also try on a little point here with the trace, and you'll see just how instantly this heats up that point. Look how much easier it is for this to heat that little point than it was on the PS5 board. All these little points are just heating up instantly. Look at that. Same with this one. It has absolutely no problem heating up each of these individual points. So you can see how 350 might actually be suitable for certain points on this board. I would still probably use a bit higher temperature personally to make your life easier. But for some of those smaller points, especially with the leaded solder, 350 is more than reasonable to be using on a small board like this, but definitely not good enough to be using on a larger and thicker board like this PS5 board. And in the same way that the size of the board you're working on or the size of the trace you're working on impacts how much heat dissipates, so does the size of your iron tip. So what we're going to do to test this is we're going to use this knife tip here that's about like 2 to 3 times bigger than the one I'm using currently on the iron. And let's compare how the exact same temperature works on the board with this larger iron tip. So let's take a look at this exact same point we've been trying out before. And we're going to use a lot more surface area on this point. And you can see just how much quicker it's able to heat the area. And it actually is beginning to melt the solder. It's not an ideal temperature still because the board is so thick and because this ground plane is so huge, but it is actually able to start melting that unleaded solder on the board on that ground plane, even though we're using the exact same temperature as we were before with the smaller iron tip. Just because I'm using more surface area and a larger tip, it is able to transfer significantly more heat into that point than the smaller knife tip. So there's that size right there. And then if I use the smaller tip here, we're going to see just how much less heat is able to be transferred into that ground point. Look at that. That's nothing compared to what we were seeing on the other side with the larger tip. Like, yeah, it's doing a little bit, but it's really not melting anything at all. And this bigger tip here is much better suited. So again, that surface area is just much better at heating points like this. So the surface area of the tip that you're using matters a ton. And similarly, if we use like a bent conical tip that's like really small like this is going to do next to nothing at that same temperature on that point there. So we're up to temperature already, and let's just see. Look, like this is doing absolutely nothing to that point. I mean, you can see a little bit of heat going in from the tip. You can see just how much less surface area is able to touch that point. But watch what happens if I put the side or the edge on it instead of the tip. See how much more that is able to do than if I just touch the end to it. If you use it correctly, you're able to put more heat into the board by adjusting the angle of your iron. So it's pretty clear that temperature here is not the only thing to consider when you're dealing with soldering. So for this point, I would actually probably be using like 425 degrees Celsius with this really big knife tip. And now let's see how good of a job this does at melting this point. You can see just how much better it is at spreading heat right into that localized area, and this has absolutely no problem melting the solder on that point there. And same with the one above it here, no issues whatsoever. It's just fully melted already. So when the board is big and thick like this PCB here, you're going to be needing to compensate for that with a higher temperature. upwards of 375 to 425, I would say, for larger boards like this. And you're also going to need to consider what size tip to use. And obviously this depends on what point you're soldering on the board. You know, if you're dealing with one of these 0201 resistors or something, you probably shouldn't be using 425. Probably 375 is plenty with a smaller tip, even though it's a big board. But you get the idea. And just make things simpler for yourself and only think about temperatures in chunks of 25 degrees. This really helped me a ton. Like if you have an iron like this here, if you go to the settings, you can often change this temperature step, which is like how much it's going to increase or decrease when you press the arrow buttons here. And I just always have this set to 25 degrees because, you know, I don't want to be pressing like a ton up and down on my iron here. I just want to press once to go between. Let's say, for example, we're here at like 425 and I just want to go down to 400. I can very easily just tap it like that and we're at 400. Or 375 or 350. And you can see just how nice a C245 iron like this is because you can switch temperatures super fast. This is actually already at 375. This is already at 400. So it takes just like almost no time at all to switch between temperatures on this thing. And it's really nice to be able to mess around with what works for you. Not to mention being able to just adjust this by 25 degrees at a time makes my life super easy. I don't have to fiddle around with like, you know, 384 degrees Celsius. Like who cares? It's really not that big of a deal. It's just getting enough heat into the board to do what the hell you want to do, you know? So I hope you guys can see like this is not like some kind of science where you need to pick a very specific temperature. It has nothing to do with picking like the correct temperature. It's really not that complicated. Now I do have to add a little bit of an exception to this here with BGA rework because with BGA rework, you're often working with sensitive chips and you're often having to put significantly more heat into a larger area of the board. So for example, if you're reflowing or replacing something like the SoC on this board or on this board, or a sensitive BGA chip like the SSD controller or these NAND chips here. These types of chips are significantly more heat sensitive than something like, say, this HDMI port here or these inductors. So it does definitely require a more sensitive touch when it comes to temperature and duration of heat exposure and the area of the board that you're heating. You definitely need to be thinking about these things a lot more when you're dealing with BGA rework. And there really are specific temperatures at which things can go very wrong when you're dealing with BGA rework. So I did just want to add that as an exception to the rule I just said. Hot air is definitely sort of its own beast. But when it comes to most other components and using your iron, it's really not that complicated and you don't need to stress too much at picking the correct temperature. You mostly just need to find a temperature that works for you as a starting point on your iron and go up and down by 25 degrees Celsius and you'll have no issues. I'll also point out that flux promotes the flow of solder, so always be using flux when you're soldering. Definitely not something to leave out. I'm just leaving it out in this video so I can better visualize how heat spreads throughout the board for you. I also want to point out that the part itself that you're working on also can pull heat away from your iron. So for example, this giant Ethernet port that we were working on underneath here is actually spreading the heat out through this entire shield, as well as the board and as well as the ground plane. So lots of things are working against you here and pulling heat away from the area. So whenever you're working with something like this, I highly recommend using hot air to actually preheat the board before you start working on it. So let's say, for example, we're trying to wick or clear the ground holes of this port right here. You're really not going to have a lot of luck with just your iron alone. Even if you mix stuff in like low melt solder or leaded solder, you're going to have a lot of trouble getting enough heat through the entire board. You're really just going to be melting it at like the top here or at the other side if you're working on the other side. So to help with this, hot air is your friend. You really need hot air. So a really great preheating temperature I always use and start at is about 250 degrees Celsius, and then you can kind of go up from there if you want to preheat the board more. But 250 is perfect just to get the board warm, and I'm going to go to like 50% airspeed. And to me, this is a great starting point for preheating. You can just kind of like take your time, get heat into the board. 250 is not going to like melt the plastic or anything here as long as you keep things moving. You just want to kind of like get the board up to temperature so that when you go to put your iron on the board, it's not going to have to do as much work to heat that ground plane, and it's going to be able to melt the solder significantly easier. So just for demonstration purposes, I'll just heat up this left side here. All right, so this area is nice and preheated. We're going to be able to see that with the thermal camera here. You can see that whole area is nice and preheated. And if we zoom in here, now with my iron, it's going to have absolutely no issue heating that point right there. You see how much easier this is? It just totally liquefies the solder instantly. And this is because the whole board here is preheated. It's not having to spread the heat around so much when the iron touches the board. It can just focus on that one point now and get it up to the temperature it needs to melt the solder. Whereas on this side, you can see it's taking a little bit longer to actually push the heat into the board. And I can already feel, even though I'm only touching this point from this side, this pin is actually fully melted all the way through the board, and I can actually push it and I can feel it moving. Even with 425, without preheating this board, I probably would not be able to do that. So preheating really helps, especially with these thicker PCBs like this PS5 motherboard here and like the Xbox Series X boards. They're really thick and difficult to work on if you don't use your hot air to preheat things. And if something's really stubborn, you can always just use both at once. So you can just apply hot air while you're applying the iron, and you'll see me doing this all the time for like HDMI port repairs and things. The other thing I want to point out here is that with portable irons like this, you're going to have almost zero luck with boards that are this thick, especially because these run at a lower wattage than irons like these, and this just means that they simply don't have enough power to put enough energy into the board when it's spreading that heat out like we saw on the thermal camera. These, even if you turn them up to the max, are not able to really compensate for that heat loss on the tip nearly as well as a whole station like this, which is going to have a higher wattage. That's not to say at all that these portable irons are useless. They're super nice for working on, for example, smaller boards like this, or just tiny points on even boards like this. But when you're dealing with big ground planes and larger components like this is not really going to do you much good, and you're really going to want like an actual station like this to deal with those types of things. Or in the very least, you're going to want a hot air station to be able to help you preheat things before you use this. So honestly, my best piece of advice is just find a starting temperature like 375 and just go from there up and down by 25 degrees Celsius and see what works. You know, obviously if you're just starting, work on stuff you don't care about, destroy things, see how high you can put your temperature on your iron before you start burning pads off the board. Especially when you get new tools, it's always a great idea to just like push it to its limits and see how different it is from maybe something else you've been using before. Because chances are it's going to behave completely differently even if it's at the exact same temperature as your old tool. So this video already got a little bit longer than I wanted it to be. So we're going to actually split the hot air temperature conversation out into a separate video. If you guys are interested in that, please let me know in the comments. I hope this video helps some of you guys just sort of like chill out on picking a specific temperature and instead just motivated you to start using your tools and get comfortable with your specific tools. Because at the end of the day, this is what this is about. It's about getting comfortable with your tools and understanding how heat spreads out and dissipates when you're using your tools with different kinds of boards and different sizes of traces and things like that. So as always, I appreciate you guys for watching, and I will see you in the next video. Peace.